All right, welcome everyone to this week's Physics Meets ML. We are very happy to have Greg Young here from Microsoft Research, and he will tell us about his recent work on tensor programs, and in particular how to use them to tune large neural networks. Yeah, we are very excited to hear about it. Please take it away, Greg.
Yeah, thanks, guys. So this is a collaboration with Edward Hu, Igor Bushkin, Simon Sador, David Farhi, Nick Ryder, Jakob Bochoki, Xiaodong Liu, Wei Zhuchen, and Jianfeng Gao. So this is a collaboration between OpenAI and Microsoft. Right, so let's get straight into it. Oh, there you go. So if you ever work with machine learning and as a researcher or practitioners, a lot of times you are exploring some new ideas, and often it makes sense to start small, right? So you explore some new idea on a small model, and perhaps you get a really nice training curve that looks like this. Everything works out nicely. But when you try to scale up, on the real deal, sometimes your model just fails to train for whatever reason, and at this point you're confused. You're like, okay, is it my idea that sucks, or is it that the hyperparameters are bad? I need to retune them. And if the problem is not too large, it's kind of small, then yeah, just go ahead and retune the hyperparameters, right? It's simple. But as you're pushing the problem size against the limit of your resources. I mean, that could mean like BERT on in academia, or in GPU3, or these like large enormous models, even in the industry, where you're limited in the amount of tuning you can do, right? And in the larger setting, you can only afford a single training run in the larger setting. So you have to come up with a way to get an answer to this question. Is it my idea that sucks, or is it the hyperparameters? And part of what this work allows you to do is to resolve this uncertainty. So if it really is your hyperparameters that are bad, then we will be able to automatically set the hyperparameters for you. And then you get a nice looking curve that looks like this for the larger model. And the mechanism behind all of this is called the maximal update parameterization, which is abbreviated MUP. And in short, it's just a principal way of scaling initialization and learning rate with the width of the model. So right now I'm going to show you this table, but don't freak out from just like the amount of text here. But for now, ignore the entries of this table. But here I just want to point out, this is just a simple encapsulation of this parameterization by specifying how to scale the initialization and the learning rates for Eschi and Adam for different parameters like input weights, output weights, and hidden weights. And yeah, the entries are just tells you how do you scale with fan in or fan out, in various ways. Okay, so that's all I want you to take away at this point. Don't worry about the details. The point here is just it's a simple parameterization. And this parameterization UP has a really interesting property called hyperparameter stability. So let's first start with the counterexample of what the PyTorch default, for example, that people use nowadays. And so in this parameterization, as you increase width, and as you sweep out the hyperparameter versus training performance curve, you're going to see a shift of the optimal hyperparameters. So the curves will increase as you increase width or move up, indicating usually you do get a gain in performance, but there's a shift to the optimal hyperparameter, so that the optimal hyperparameter for the smallest model is necessarily optimal for the largest model, and you're leaving money on the table by not doing any like the principal way of doing it. On the other hand, for MUP, you get this really nice curve that the optimal hyperparameters for different model sizes, they all align, so you can use the best hyperparameter for the smallest model, and they will also work and is near optimal for the largest model. So that was a cartoon, right? But in practice, actually, it's actually very close to what the cartoon shows. So this is a actual transformer trained on Wikitext2 via Atom. And on the left, we have, again, using the default parameterization. And when we plot the training loss versus learning rate, so here is inverted from the last slide where it was performance, so higher the better, but here is lower the better. But anyway, in the left, you can clearly see that there's a shift of the curves to the left. So this indicates that the optimal learning rate shifts become smaller and smaller as it goes. Whereas in μp on the right, the optimal learning rate is stable, right? So this is much more desirable on the right. And furthermore, if you just look at the absolute best performance for the largest model, μp will have an advantage over the existing default. And here in particular, if you're taking the best learning rate for the smallest model and you're using it on the largest model, you can see that like you would just kind of diverge, you would do much worse, right? And this is a possible explanation for when you see this kind of phenomenon where when you scale up, things kind of just break. So using this insight, we propose a very simple method for tuning hyperparameters on extremely large models. And the gist is just that instead of directly tuning them, which is infeasible, you just shrink the model using along μp, tune it, and then you transfer the hyperparameters back. We just essentially copy the hyperparameters back to the large model and then just run it, right? And now you don't have to ever touch the large model until you actually want to train it, rather than you have to touch it. You have to train it multiple times during tuning process. So we call this mu transfer. In our paper, we carefully validate all of the above science and methodology from small settings like CFAR10 MLP all the way to GPT-3. So to summarize, μp has this interesting property of preserving hyperparameter optimum across width, and it allows zero-shot hyperparameter transfer. And this gives you efficient tuning of neural networks, really of any size, but especially of these enormous neural networks, which you might not even be able to fit on a single GPU. But we can tune it on a single GPU, which is kind of trippy if you think about it. And this is very, very fast. So and at this current moment, it's the only way, as far as I know, for tuning large neural networks. And altogether, this is like a very, I think, essential tool for in any toolbox dealing with reliable scaling up of neural networks. All right, so this is all I'm going to say about an overview of μp, but at this point, I want to take like a large step back and just kind of look at the overall picture of this field at the moment. So I want to, talk briefly about what space program and Manhattan Project have in common. One, of course, they're like very impressive achievements of humankind in the last century. But in particular, what I want to point out is that each empirical test here is very expensive, right? You can't just keep launching space shuttles every day, especially if you have human on it, without like doing a lot of preparation, right? And because it's so expensive, we require a lot of extensive theoretical calculation first before launching any empirical test or empirical run. And I will argue that today, with large pre-training of language revision models, we're in a similar regime, not the same scale because we're off by like 1,000 times in terms of costs, because space program costs like 10 billion or something dollars, where these models maybe cost like 10 million or so. But we're definitely in the same regime where each training run of these models take quite a while to prepare. and it's not something you can just launch every day. And you need to do a lot of work to ensure that you are able to train them reliably and optimally. And as we saw in the beginning, this is really not trivial at all. When you really get your hands dirty and try to make it work. So that's kind of the key question. And what I want to point out here is that in deep learning is very much empirically driven field. And when you have a lot of compute, empirical insights are cheap, and especially on problem scales that are small. But if you look at theoretical insight, it has the characteristic of being like roughly kind of constant in terms of cost, even as the problem scale changes from really small to extremely large, right? Whereas empirical insight, they are more and more expensive to obtain as the problem scale becomes larger. So on something like CFAR10, like small classification data sets, empirical insight is pretty good. Like you don't need to really think about anything theoretically at this scale. But when you're going to these large scale pre-training, and like as a comparison to space program, like these things were places where the right theoretical mindset and right theoretical way of thinking about them really matters. And this is where MUP lies at the intersection, where it has the most leverage at the intersection of theory and large scale pre-training. Okay, so that's all I'm gonna say about MUP as an overview and also kind of like this larger picture. Any questions so far? All right, so the plan next is I'll talk about what actually is MUP, like explain kind of the entries in that table we saw earlier. And then I'll talk about what hyperparameters do we cover in our framework. And I'll talk about some of the empirical results we obtained. And finally, I'll talk about the theoretical foundations that are involved in this work. Okay, so to explain MUP, I want to do this via an example. I think that's probably the most instructive way of doing it. So let's look at a neural network, a 3-layer neural network with 3 weights, W1, W2, W3. And the width model, I'm going to denote it by N, and the data dimension denoted by Dn. Okay, so in the standard factorization, right, the PyTorch default, whatever, the weights are initialized or sampled randomly initialization with a variance something like 1/fan-in, right? So typically you'll see sampling that looks like this. So first layer weights has a variance 1/dn, and second and third weight have a variance 1/the width because that's a fan-in, and the biases are 0 and learning rate is eta. Let's denote it by eta. Okay. So if you try to sweep this value eta for different models of different widths, you're gonna get curves that look like this, right? So as the model increases in size, which corresponds to darker and darker curves, you're gonna see the optimal learning rate decrease to the left, right? And in particular, if you look at the best learning rate for the smallest width, is going to do kind of quite badly for the largest model. So that's not good. All right, so let's look at what mu parameterization does. So the main modifications here are in the output layer W3, where we scale down the learning rate by factor of width, and then scale down the variance of initialization also by factor width. And in addition, we scale up the input and biases learning rate by factor of width. Okay, so this is probably kind of strange at this point. So I'll explain this. I'll explain why do we make these modifications. But if you just take this parameterization as given, and then again you sweep this the learning array here, the data here, you see like really nice looking curves that looks like this, where the optimum they do align across model sizes. So you can use the best learning rate for the smallest model and use it on the largest model, right? I see like maybe is it a question in the chat?
Yeah, I think there's one which is saying, isn't there are different initialization default in PyTorch, K-Ming?
No, actually, timing is not the default, but that doesn't really matter here. Like I'm only talking about scaling. So ignore the constants like the ones here. Like that can be anything you want. So timing would have like instead of 1, you had 2. But that's kind of tunable. It's a tunable hyperparameter. But what I want to focus on is the scaling here. Especially with n, right? Hopefully that answers your question. Okay, so now let me explain why we make these modifications. Okay, so in particular, I'm going to focus on like the output layer modifications, and yeah, maybe I'll say a little bit about the input layer modifications later on, but I'm going to focus here on the output layer. And the question is, why do we scale down the learning array and the initialization, right? Okay, so to make my point, I'm first gonna just do a trivial thing where I write out the output of the network. Here is expressed as a matrix product, but I'm just gonna write it out, write this inner product out as the sum over the neurons from 1 to n of the output layer weight entry times the embedding entry. Okay, so you can do a little bit of calculation yourself, or make it easy for yourself and maybe like assume phi is a hyperbolic tangent or something like that. Then you'll see that like this, the entry here, phi or whatever, this is a constant size object. And this like 1 over these modifications, that this lowering of learning array, for example, this ensures that the W3, the output layer entries, has size 1 over n, right? So for example, like the initialization being 1 over n squared ensures that initialization is true, and then the learning rate being 1 over n also ensures that during training continues to be true. Now the point of making this modification is that when you sum up these things, right, you're summing up n things, and each of size 1 over n, if you don't have any cancellation or any major cancellations, or like if you have you don't have independence, or like strong lack of correlation, then you should expect the sum to be a constant size object. And this is indeed what would happen because during training, like after you take gradient steps, this upper layer and the embedding fees entries will become correlated. So you have correlation, and that will mean that when you sum them up, the law in effect is the law of large numbers, not the central limit law. Okay, all right. So this probably sounds like super trivial. It's like, you're probably like, okay, like, why are we doing this? Probably this is already taken care of, right? Like by the default, no. But it's actually not taken care of by the default. So in the default, essentially you don't have these modifications. For example, learning rate is just a constant learning rate for the output layer. And if you do the same calculation, you see that like after a couple of steps of training, like the output layer entry is constant size. So when you make the sum, from 1 to n, you get the output is a size n object, right? Not size 1 as in mu p. And part of the mistake here is that the standard parameterization was derived only for initialization, and then they didn't think about training and the correlation that can arise during training. So that's not good. Okay, I see a question. Okay, I don't get the modified function form. Do you want to say something? What do you not understand? Sharma? All right. Maybe you can ask us later. Like, if you don't want to speak out now.
It's in the chat.
Yeah. Oh. No, I mean like yeah. I read the chat and then like I guess what is there? What is confusing? What particular is confusing about the functional form? Okay. I can't even click the chat right now.
Can I ask another question while we're trying to find it?
Yeah, sure.
So in my understanding, I don't remember details, but basically standard parameterization now Xavier or K-mean initialization, which differs only by type of activation function. So the purpose of this initialization is to save the mean and standard deviation of output when you increase the depth of the neural network. So and here in your standard parameterization, you basically you show that the output increases. So basically it should not work because you will have exploding gradients or vanishing gradients. So basically the problem which
so you're conflating two things. So you're right that like Kai-mean is derived for preserving like the activation scale when you're initializing and when you're like training a deep network, when you're scaling the depth of the network. Okay. Here we're in this particular example, we're fixing the depth and we're scaling the width of the network. Does that make sense?
Yeah.
So that's one difference. And then the other thing is we're really talking about like what happens during training. Like talking about initialization is kind of simple in some sense, right?
Exactly. It's important point that everything becomes correlated, and you cannot use central limit theorem anymore. But I mean, my question. So if you change this type of initialization, how your distribution of how the picture changed from point of previous initialization? I mean, when you increase the depth of neural network. So here you change the learning rate for different layers, and it seems like you are coping with this situation exactly by having different scales, right?
Yeah. So you mean like what is the right parameterization when you have more than 3 layers, for example? Is that the question?
Yeah, exactly.
Yeah. Okay. Yeah. That's essentially the next slide.
Okay.
Yeah. Okay. So let me briefly answer this question, and then I'll also look at the chat after that. Yeah, this table essentially you saw at the beginning already, but this encapsulates what is like what to do in general. So essentially, we divide in the general case, you divide the parameters into input weights and biases, output weights and hidden weights, and then you scale initialization or the learning rate according to entries in the table. So in particular, the first 2 rows, are kind of just correspond to whatever I wrote in the previous slide for the 3-layer case, where like 3 layers are the input, output, and hidden essentially. So that recapitulates the example previously. But here I have additional row for how to scale atom learning rate, and of course, like that's kind of in practice that's quite important because outside of like CFAR10 or ImageNet, pretty much everything uses atom. And then the other additional thing here is for transformers, there's changing to make it to the attention, where attention is k times q over d instead of square root of d. And again, this is just due to the fact that once you start training, there's correlations, and so there's a square root of d factor when you account for that. Okay, let me look at the chat. So bad formalization kind of like a band-aid, and it will help alleviate the problem, but it doesn't solve the problem. And so here, in particular in this example, when we don't have batch normalization, the effect is very obvious. But also, we'll show you examples of, transformers where we have layer norm, and you see the effect. I mean, actually, you already saw the effect in the beginning, right? Like where the curves are shifting already, and that has layer norm, and so it doesn't help. You have to solve the fundamental problem.
Can I ask something about Adam here?
Sure.
For Adam, I wondered whether the initialization is so important, because Adam will remove these fixed factors anyways because of its normalization, right? So
yep.
Can't I leave away the initialization changes you made if I want to use this?
Like just ignore the first row? Is that what you're saying?
Yes.
Yeah, I think probably you'll do like fine. Like you can probably like not suffer like any dramatic problems until like your width is extremely large. Yeah, so I'd probably say in practice, like you can probably like you don't need to do this if you don't want to, but I think you probably will affect the transfer quality. So remember, like in the end, what we care in this work is to be able to tune the large model accurately using the small model, right? So for that, you want to be as kind of like accurate with your parameterization as possible. But if you just care about training like stably, then yeah, probably you don't need to use the first. You don't have to parameterize this as much as the learning rate, as important as the learning rate.
Thanks.
Learning rate, layer norm does not change the scaling prescription for hyperparameters. So everything here still works with layer norm. Okay, so I'll leave Edward answering the questions in the chat. But if you want to hear an answer from me, just shout it out. Okay, so now I'm going to talk about which hyperparameters can be transferred, and usually in general, like how do we think about hyperparameters in this framework? All right, so at the highest level, you can think of hyperparameters as one of the two groups. One is the compute hyperparameters. So if you look at the right column, these are examples of compute hyperparameters. These are ones where when you change them, you change the cost of your training process, where the size of the model, right? Like this is where like, you pay a monetary cost when you change these hyperparameters, or when you make them larger, for example. And then there's the non-compute hyperparameters, which are the two columns on the left. And roughly speaking, you can divide them into like regularization or focused hyperparameters versus the ones that are not regularization. So optimization, related, initialization, parameter multipliers, roughly speaking. Okay, so the way we want to think about this is that we want to transfer the non-compute hyperparameters across the compute hyperparameters. All right, so we want to shrink the model width with the model depth and so on and so forth. And then we tune on the smaller version of the model, and then we pop the hyperparameters back to the large model, right? So we want to transfer across the compute hyperparameters. So then it's natural to ask, okay, well, like what within non-compute hyperparameters, what can we transfer? And roughly speaking, the answer is that we shouldn't expect to transfer regularization at this point for a very natural reason. I'll explain shortly. But pretty much everything else is should be fair game. So let me explain why. Regularization, is used essentially when you don't have a lot of data, and especially when your model is large compared to the data size. So naturally, like if you want to be able to transfer regularization, right? Like as in, if you want to be able to, make sure that the optimal regularization for small model is also optimal for the large model, then you really better know not only the model size, but also the data size, right? but μp as designed doesn't know anything about data size, so you shouldn't expect to be able to transfer regularization. So if regularization is really the bottleneck of the performance of a large model, then MeP may not help with that. But luckily for large scale pre-training, we still have too much data, so regularization is not a bottleneck. So far we kind of mostly talked about model width as a compute hyperparameter to transfer across. This is where like there's a lot of theory, theoretical guarantee, for example. But the natural question to ask is, what if we want to transfer across depth and batch size, training time, so on and so forth, right? We don't have any theory for those at the current moment, but we just empirically explore transferring across those things using naive methods. And we'll see that like they work, the naive methods will work across reasonable scales of problems, or like reasonable depths, for example. And I'll show you some plots for this. But if we really want to go to extremely larger sizes, right? Like we really want to have a good theoretical understanding of this problem. Okay, so now I'm going to show you some verification of the hyperparameter stability across width. So here I have two kinds of transformers: post-Layering transformer and pre-Layering transformers. I don't worry too much if you don't know what they are. They're just two common kinds of transformer models. And I'm plotting the training loss versus the optimal learning rate, the optimal cross entropy temperature initialization, so on and so forth. Like these are the kind of representative hyperparameters that you want to tune, right? So the point here is that, as you can see, is kind of similar to the previous plots you've seen, but the optimal learning rate, for example, is quite stable with respect to width, and as well as all the other hyperparameters, right? So like this kind of verifies what we expect theoretically. Okay, so now this plot kind of goes a bit further, and you can ask, okay, yeah, we can maybe like double the width for all the hidden layers, but what if we want to like vary the width ratios, like double one layer and then quadruple the next layer, right? So on and so forth. And this is just to verify that you can do that. You can like change the width ratio arbitrarily, and we can still maintain the optimal learning rate, for example, is still stable when you make these changes. Here, we are just trying to demonstrate that in transformer, you have kind of two notions of width, if you will, the dimension of heads and number heads in the self-attention layer. And here we're just demonstrating that, oh yeah, if you can fix D head, you can vary N head, or you can fix N head and vary D head, or mix match, and everything will still work. And finally, this is I think a really interesting property that in some sense we didn't really expect, but at this point it's so robust that I think we think this is kind of like a fundamental property. So the property is that if you fix the hyperparameter, your hyperparameter combination in MUP, and you increase the model width, then you see that the curves never intersect, right? So here we're plotting like the loss curve versus training step, and you can see that the curves don't intersect. This means that you don't have a situation where going wider does worse, right, than than like a smaller model. But this is not true in standard parameterization. So if you use small learning rate in standard parameterization, and you might get the illusion of, oh yeah, this is true, up to some width. But then if you try to go even wider, you just get like much worse performance all of a sudden, right? And this is, if you don't know about this phenomenon, you're probably like, okay, WTF, like what happened here? Like, did I, is it a precision issue, whatever? right? But really, it's just a parameterization issue. It's like just like the mathematical issue. It's not like a hardware issue or something like that. Yeah, and for if you just use a large learning rate in standard parameterization, yeah, you can already see this effect where going wider actually gets you strictly worse performance. Okay, so that's what I'm going to say about width. And now I'm going to talk a little bit about, again, the empirical results we have for transfer across depth and other dimensions. So here, again, we're not claiming we have any theoretical understanding of this thing. We're just trying to answer the natural question. Okay, we can do width. Can we, do some like reasonable thing across these other dimensions and get like reasonable results? And the answer is, for the most part, yes. Okay, so in particular for depth, then the bad news is that it doesn't work for a post-linear norm transformer, and this is like completely within expectation of the community understanding currently, because like this is like a common wisdom at this point that post-linear norm transformer doesn't work well, or it's hard to train, it's difficult to train when you have a deep version of it. So this is completely within what we expect. But for pre-linear norm transformer, it does work reasonably well. So here we're going from depth 2 to 32, and you can see that like the optimal learning rate, whatever, learning rate schedule, so on and so forth, they're all relatively stable with respect to the depth. And we will apply this to when we do our experiment on BERT. And then here are kind of plots for the other dimensions. So like batch size, sequence length, training time. And yeah, again, this is for pre-linear transformer. Again, you can see that the optimal hyperparameters more or less is stable with respect to like these batch size or whatever, these compute hyperparameters. And likewise for post-linear norm transformer. Okay, so I see there's like a lively discussion in the chat, but I'm letting Edward handle. If you want me to answer any questions, feel free to shout something out. Okay, so at this point, I'm gonna start talking about the empirical efficacy of the mu transfer algorithm for actually tuning hyperparameters. So previously, we were just verifying that the science or like our hypothesis of hyperparameter stability is correct. And here we're like actually trying to push the limit of this technology for tuning large neural networks. So we did a lot of experiments on models of different scales, but here in this talk I'm just gonna start with IWSLT, which is a relatively smaller machine translation data set where we can do more science because it's smaller. Yeah, so this is just another plot showing, okay, yeah, on this data set, standard parameterization still doesn't work as you expect. So I'm gonna skip over that table, but I'll show this instead. So we essentially repeated many trials of mu transfer, tuning models over and over again, but with different tuning budgets, which is plotted on the x-axis. So they're like relative tuning budgets to some baseline tuning budget. So this is flops. So we're fixing the total flops cost of tuning. So this means that if you tune directly on a large model, you can only try like a small number of hyperparameter combinations. But if you tune on a smaller model, you can tune more, right? You can try more combinations. And here the orange curve is the conventional approach of directly tuning on the target model versus our approach, which is the blue curve. And this is using mu transfer, right? So in particular, we shrink the target model by 4 times in the width, and then we tune on this smaller model, and then we just copy the hyperparameters to the large model and we evaluate it. And because we're shrinking the model 4 times in width, we can tune about 10 times, 12 times more hyperparameter combinations. than directly tuning on the large model, given a fixed compute budget. So, yeah, so we repeated this over again, like for many trials for different compute budget, and so finally we plot the Pareto frontier of the budget, compute budget, versus a quality model, where like the higher the better here. And you can see, like for example, given the fixed model quality, you can expect maybe like a 10 times more efficient tuning procedure. And so this is great. It's like a really neat, gives you a really neat picture of the potential efficiency of our method. But in fact, this is actually an underestimate of where it can be most effective. So again, because because we want to do science, we're doing this experiment on a smaller data set and a smaller model. But for the largest models, these can be like 200 times bigger than this, and our efficiency only goes up. It's directly proportional to the ratio of the size between the target model and our proxy model, right? So this is like strictly underestimate of where you would be most effective. Okay, so that's the IWSLT. Next, I'm going to talk about BERT and then GPT-3. So this is where like we're really applying our technique and try to see like how far we can go on like data on like actual large models that people care about, right? So for BERT, mu transfer essentially is as you expect. So we create a BERT small by shrinking both the width and the depth of the model, and we tune the small model using 256 random combinations. So we try 256 random combinations of hyperparameters, and we just essentially tuning it and then like obtaining just asking which random hyperparameter is the best among these. It will give you a reasonable estimate of the best hyperparameter combination in the entire hyperparameter space. And here we're only tuning, when we tuning, we're only training for 10% of the total training time. We would actually train for the target large model. So in some sense, we're shrinking both width and depth as well as the training time. And then finally, we just copy the best hyperparameter combination to BERT base and BERT large. So in particular, note here, we're only tuning once on BERT small, but we apply like the hyperparameter to both BERT base and BERT large at the same, at once, right? So we're not paying twice the tuning cost. And this is because we can both BERT base and BERT large shrink to the same small model. And again, here is where we're combining our theoretically motivated width transfer with depth transfer and training time transfer that we evaluated empirically. So it ends up that the total tuning cost is equivalent to 1/4 training run of BERT large. Okay, so this is the result table. I'm not sure folks are familiar with the numbers, but let me just point out two things. So we're comparing against the Megatron default, which is a well-tuned BERT baseline. So it's actually a stronger version of the original BERT. So we're not comparing against some weak default. And so you can think of this as like a strong baseline of what manual tuning would entail, previous to our method. And we also compare against naive transfer, which is just, you try to transfer, but you don't use NUP, you use standard parameterization. And as you expect, on the large model, the training would diverge. So, yeah, so that's one thing. And the other thing I want to point out is that you can see the improvement from mu transfer is larger for the large model compared to the base model, right? So in other words, the larger the target model is, the more we're gaining in performance. And this totally makes sense because the the larger the model is previous to the transfer, like there's just no way of tuning them. So, and you have less resources to try hyperparameters, right? So it should be kind of obvious that the larger the model is, the less well tuned it is. Okay, so that's all for BERT.
I have a question. Sorry,
yeah,
if I
go
may.
ahead.
So with what you're saying, then kind of if we go to extreme, what you would do is you would just train with one and then expand it to like whatever width you want, but that probably wouldn't work.
Yep.
So like, have you tested how far you can go in that regard?
Yeah, so so that was kind of implicit in the plots I showed earlier, but we usually recommend, like, I say 256, 128 are pretty safe choices. It gives you pretty, I would say, like, gives you pretty accurate estimate of the optimal hyperparameter, but they're not, it's too small, that is really noisy. It's not too large that it makes the model too big to tune. So so that's our recommendation that we write in the paper. Does that answer your question?
Yes.
Excuse me, I also has a question. You mentioned before that we need to change the square root d in the self-attention to d. Like, did you change both the naive transfer and the mu transfer?
No, this is naive. Just means like the original, just the original. We don't touch it, and the mu transfer is ours. It's just with everything in there. So we did not ablate, I guess, like individual changes, because I mean that doesn't really make sense, right? Because like mu p is like, it's a whole package.
Okay, and then I just wonder, does the change from square root d to d will just improve the square here instead of the mu transfer? Like, you've changed the
yeah, possibly, but I wouldn't expect the improvement to be large.
Okay, thank you.
Yeah. All right, so now let me move on to talk about GPT-3. So this is an interesting case where the way we collaborated was we never saw their code from the OpenAI side, but we advised them on any questions they have. But they essentially just understood the the technique, the kind of the math behind it, and they they thought everything made sense to them, and they just implemented it themselves on their own custom code base. So it's kind of like, so everything here is kind of like a held out set that verifies that everything kind of works. It's not just our own code setup, some quirks involving our own code base on the Microsoft side. So they replicated several experiments on their GPT-3 model. So for example, the stability of the hyperparameter optimum, and also the fact that wider is always given, is better given same hyperparameters. Okay, so then finally we scaled up and actually applied mu transfer to the 6.7 billion parameter model of GPT-3. And so if I recall correctly, I think we transferred from a 40 million parameter model to a 6.7 billion parameter model. So that's like a 100 times shrinkage. And so this would mean that if you actually try to replicate what we did on the tuning we did on the small model directly on the large model, it will cost you at least 100 times more, right? And that's like entirely infeasible. So in the end, the total tuning compute budget is only 7% of training budget. So this means like the flops we spent on random hyperparameter search on the small model, it only amounts to 7% of the actual cost of the full pre-training run of the 6.7 billion parameter model. So this is rather small, and as you go to larger sizes, it will become even more and more negligible. And in terms of quality of the model, we essentially beat so the plots here show so the plus mu p is our version, and then the without the plus mu p is from the original paper. So on the left we compare against the same sized model, and on the right we also additional compare against the 13p model. And on the left we don't have the 13p model because there's no these numbers for the original model, and this is like a rerun of the original setting. And it just is we handily beat the baseline, so 6.7 billion parameter model. But in fact, we like perform comparably to the model that's twice as large from the original paper. So you can kind of see it here. So this actually like, so we selected some like standard tasks for evaluation, but so here it shows, like our model is actually seems like it's like quite a bit better than even a 13B model. But if you look at like a suite of evaluation across, like 40 tasks or whatever, you'll see that it's actually kind of balanced. They're comparable. Okay, so I guess one thing I should mention here is that the science here is not as solid as we want it to be, because the code base for GPT-3 has evolved since the original paper. So we try to do a rerun of the original paper in the new code base to ablate the possible effect of the code base changes. So like, for example, the 6.7b numbers here are actually from the new rerun we wanted to do for we wanted to use for ablation. But there were like actually like a couple of things like attention that was using the old settings at the new setting. So we didn't actually cleanly ablate all the changes in the code base. So like strictly scientifically speaking, I probably can't really exactly confidently say like everything can be attributed to mu p, but I think that the improvement is just way too large to be probably like some code changes. So in particular, it's like attention, absolute versus relative attention. So so yeah, just an FYI. Okay. All right. So I guess we're 5 minutes till the allotted time, but I'm gonna talk about the theoretical foundation next. And I guess if people are interested, feel free to drop out. Or if anybody has a question now you want to ask me, you can take a jab.
There's a question from Eva in the chat. I'm happy to read out, but ask it.
Sure.
Yeah, so here's a more far out question, but I'm curious, does it suggest that the variance or more general statistics of synaptic weights in animals of different brain sizes will vary in a certain way with size? Might this be measurable in neuroscience experiments? Probably that requires a version of Hebbian learning or whatever the realistic learning dynamics is in biological neural networks.
Yeah, I mean, I think the general lesson here is just if you think about like if you think about like neural network, whatever general systems of varying size in the right way, if you kind of align model of different sizes in the right way, then like there's like you can preserve like kind of like the really coarse properties of these systems even as you vary the size, right? So here is like optimal learning rate or optimal hyperparameters. But I mean, this is like a general principle, right? Like if you like kind of look at the systems of different size, in the right way, right? Like they kind of preserve certain properties. I mean, it's kind of like self-similarity. It's kind of like renormalization in some sense from physics. So so if you want to go that far into the brain, I think you don't need to really even think about like what I said here, because it's really a general there's a general like phenomenon behind all of this. All right, so yeah, let me go on perhaps and I'll talk a little bit about the theoretical foundations. So first of all, I want to kind of just lay down what exactly I mean by parameterization in all of this, right? So like the kind of the hero of our story so far has been mu parameterization or maximal update parameterization. But in general, what is a parameterization? So this is a table from before. And in some sense, in a rough sense, you can understand parameterization as just like some way of filling this table in terms of in terms of how do you scale different initialization or learning rate with fan in and fan out. That's like roughly 99% captures the notion of parameterization. So in particular, the parameterization tells you how to scale hyperparameters when model size changes. So for example, we can say half the learning rate when the width doubles. But I want to point out that it doesn't tell you how to set specific values of hyperparameters at particular model sizes. So it does not say use learning rate 1-3 at width 1024. Okay. And finally, the way I'm defining parameterization means that for any fixed model size, all the parameterizations are equivalent up to tunable hyperparameters, right? These hyperparameters include, constants in initialization variance or in the learning rate, right? So when you fix a model size, like all the fan in and fan out, they're constants, right? So like they can all be tuned away. So in other words, when you optimize all the hyperparameters over a fixed model size, right? There's one optimum for all the parameterizations. So one way to think about it is that parameterization gives a way for expressing hyperparameters, just like a basis gives a way to express vectors in a vector space. And a priori, like there's no canonical parameterization, even though there's like default in PyTorch, but like kind of mathematically, if you think about it from first principle, there's no canonical parameterization. Just like a priori, there's no canonical basis in the vector space. Okay, so the second thing I want to point out is that a parameterization, every parameterization corresponds to some kind of infinite width limit. The limit could be bad limit, it could be good limit, but in general, you can always take an infinite width limit once you have a parameterization. And conversely, like an infinite width limit is kind of defined by a way to take the limit, and the way to take a limit is defined by parameterization. So for example, NTK parameterization will give you like NTK limit, and then maximal update parameterization gives you this feature learning limit. All right, so given this, I hope this is not confusing, or like hopefully there's no question so far. Okay,
yeah, I have
so
a quick question, if you don't mind.
Yeah, sure.
Yeah,
go speak. I'm gonna get water.
Yeah, cool. Just in this MLP case that you were talking about in the beginning, and now returning to the theory, I mean, whether you get that 1/n versus 1/n squared scaling, I mean, affects, for example, the 2-point function heavily. So like in the normal NNGP story, you get a kernel that doesn't depend on n precisely because of that scaling. Whereas here you're doing something different, and you talked about replacing the CLT by the law of large numbers. Could you maybe just say some more and give some intuition? Because
yeah,
I mean, scaling is strongly affecting the statistics of the neural network ensemble.
For sure, yeah, for sure. So yeah, so you're right. Like when you make that modification initialization, when you scale down the initialization, your model is going to converge to 0 at initialization. So like the initial GP is kind of like, in some sense, we don't care. And you can evaluate, actually, you can, okay, so actually, like when we train models, we actually just initialize the last layer to 0 most of the time. Actually, like, yeah, I think we all, yeah, unless like there's a specific reason not to do it, like we usually initialize last layer to 0. And I'm not saying this is like standard across everybody in the community, but this is like how we do it. And it does not affect performance whatsoever. So like my point is that the initial GP doesn't kind of matter if you don't care about uncertainty and all these other stuff. If you just care about performance, it kind of doesn't matter. And the scaling down, doing training allows you to avoid this kind of blow up in the output layer. Like essentially, in the original, like the standard parameterization, without this downscaling initialization, you can't use a large learning rate for the body network because it's going to interact with this initialization and then blow up the output of the network. Does that make sense? So this is kind of into one reason we're doing this downscaling.
Okay, so I mean, I think you're saying is that the intuition is that the extra 1 over n keeps things from exploding too much as you train, as opposed to it really mattering at initialization. The point is to get the extra 1 over n during training.
Yeah. The point is to not let initialization prevent you from using a large learning rate.
Yeah. Good. Thanks.
Mm-hmm. Yeah. Okay. So given this, we have what I'll call the optimal scaling thesis, which is a hypothesis that we have an equivalence of the following. I mean, I'm not phrasing this in a very rigorous way, but I think this gets the point across. So on the left side, we're saying that if a parameterization preserves hyperparameter optimum across model sizes, if and only if on the right side, its limit maximizes future learning and without blowing up the training and so on and so forth. So one thing you can note here is that the left side is kind of something useful empirically. You can verify empirically, like in the plots we have, whereas the right side is a theoretical property of the parameterization, right? So this is like, so if you believe in this thesis, it gives like a very nice bridge between something like we can show or calculate theoretically, and something that's useful in practice and we can verify empirically. And the way I'm phrasing this, in this form, actually is kind of agnostic in terms of model size. So the model size can be width, can be depth, or number of experts, or whatever, right? There are many notions of model size, but I think this scaling thesis, optimal scaling thesis, should be true in general, regardless of the notion of model size. But here, of course, we're only like our paper is only mostly focused on width, right? Like the theoretical part is only focused on width. So, like kind of talking about this in a more general setting for depth and other things are still haven't been done yet. So to demonstrate this thesis, here's a animation. So here, we're kind of interpolating between μp and the PyTorch default parameterization by interpolating the initialization and the learning rate scaling, right? So this gives us like a 2D plane on the right. And this is a 2D plane of interpolated parameterization. And on the left, essentially, we're kind of doing the same curves we saw earlier, where we sweep models of increasing width over different learning rates. And the key takeaway is that, right, like essentially only when the parameterization is MUP, you see like an alignment of the optimal learning rates. And in particular, in the PyTorch default, you get this like shift, right? And also in general, like the performance is just worse when you're using the PyTorch default versus MUP. Okay, so again, I hope this kind of at least convince you that this for width optimal scaling thesis is true. So now I'm gonna like quote unquote prove this thesis for width. It's not actually gonna be a rigorous proof, but I think gets the point across. So this harks back to the dynamical dichotomy theorem from the previous paper in the series. So this is a classification theorem of like kind of the possible like natural parameterizations you can give to neural networks. And so this is like this picture right here in particular is a depiction, a caricature of the space of parameterizations. So for example, like the points can correspond to a neural tangent parameterization, or a standard parameterization with different learning rate settings, or like MUP. Let me kind of like go through what each region means, because we'll use this theorem to prove the optimal scaling thesis. So most of the space, this gray area, is either unstable or trivial. So what that means is that when the width is large, where you're in the limit, the parameters, like the points in the space, which corresponds to parameterization, will lead the model to blow up if it's unstable, or it's gonna make the model get stuck in initialization, and like essentially nothing happens during training. And we say that's trivial. So if you throw a dart in the space, you're most likely gonna hit one of the either unstable or trivial parameterizations. So the more interesting ones are in this middle polygon here. And bulk of this space is in the kernel regime. So what this means is that in the limit of infinite width, the function evolves according to a function equation, like this, where the change in the function is equal to, like, negative learning rate times the kernel, some kind of kernel, times the loss derivative of the function. Okay, so if you know anything about neural tangent kernel, like this is very familiar. But the crucial thing is that there's no feature learning done here. All the features essentially fix initialization effectively. Okay, so that's the kernel regime, and then there's like two pieces of boundary of this that forms the feature learning regime. And here, the network will do feature learning, and in the infinite width limit, and also the function evolution cannot be described purely in the function space. So here, for example, you have a description of the evolution purely in the function space. In particular, it's like a linear equation in this L prime. But in the feature learning regime, you cannot. There's no description like this in purely in function space. Okay, so that's a summary of what this dichotomy theorem says, and now we're going to use it to prove the optimal scaling thesis for width. Okay, so it's the proof essentially by process of elimination. So obviously the unstable trivial parameterization will never give you hyperparameter transfer, right? Because if it's unstable, then the optimal learning rate will converge to 0. And if it's trivial, then the optimal learning rate will diverge to infinity, right? So like, that's never going to work. Then we have the kernel regime parameterizations, and that's not going to work because in general it has like the performance will like get worse at some point after you hit some width. So in particular, for example, in TP4 in the previous paper, we evaluated NTK on Word2Vec has like trivial performance, right? So like it doesn't really make sense at all. It doesn't make sense that kernel regime parameterizations would ever transfer hyperparameters. Okay, so now we're left with the feature learning ones. And if you look at the non-maximal feature learning limits, so the ones that are not μp's limit, the difference from μp's limit is essentially in that some parameters are not trained and they're stuck to initialization, even though like the learning rate nominally is like non-zero, could be like 100 even. But in the infinite width limit, like there's some scaling factor that effectively makes the learning rate go to 0. And as such, like in finite networks, learning rate for those parameters, obviously has a non-trivial effect, and there's like optimal and non-optimal learning rate. But in the infinite width limit, like all that goes away because like the learning rate is effectively 0, right? So like obviously there's, you cannot expect transfer to happen for those hyperparameters. So the only thing left is μp by this process of elimination. Okay, so that's my proof for optimal scaling thesis for width. And this is like general, right? This is, if you fix any architecture, you can make this argument.
Sorry, Greg, can I ask you? So you lost
go ahead.
in some sense. So what's the argument that that's really singles out μp here? So you
mean like the like the whole argument or just the last part about like the non-maximal?
The last part, in some sense, right? So you are comparing essentially
Mhm.
the different kernels that you're getting, and you seem to try
Different
to make an
feature
argument.
elements. Yeah.
You're trying to make an argument that mu p or is the optimal one here, or the kind of stands out. Yeah, can you comment a little bit because you're making a particular choice, as far as I understood, for mu p effectively, right? You're making a particular choice of scaling that you're taking.
Yeah.
And it's very interesting to understand why why that stands out, because
yeah. So a result of the previous paper is that within the feature learning parameterizations, if you're not mu p, then you differ in mu p only in that effectively some parameters are not trained. For example, the input layer is stuck in initialization. Okay, like the learning rate for the input layer has no effect in the infinite width limit. So you, for example, like if your parameterization, if your learning rate for the input layer is scaled down by a factor of n compared to mu p, you will still get feature learning in general. Like your other layers can learn features, but essentially for the first layer, you're just stuck in initialization, right? So in that case, it's kind of obvious that you cannot transfer hyperparameters, especially for the input layer. But in general, if you count anything containing the first layer learning rate, like this combination, you cannot transfer, right? So that's a consequence of the classification theorem, that like essentially anything that's not maximal in the feature learning regime differs from UP by just not training some layer.
Good. Yeah, thanks.
Mm-hmm.
I have another question, if I may.
Yeah.
So mu p, you basically scale the learning rate by, I think it was a factor of n, and you also scale like some layers by a factor of n, so that you would get a constant, an O of 1, if I recall correctly.
Mm-hmm.
So what happens if you, for example, so let's say you do, like basically what you want is you want some kind of cancellation. So what happens if you do like n square, like you scale things like not with n, but like n squared and something like that, so that you get the same cancellation? Would that still work?
What do you mean by cancellation here?
Can you go back to almost the very beginning? That's okay.
Yeah, let me see.
It was one of the first slides you had.
Yeah, I'm trying to see if there's like a easier way of maybe this. Let's see all slides. Like this slide.
So yeah, for example that one.
Yeah.
So you're scaling the learning rate by fan out, or let's look at fan in. So you scale the hidden weights by 1 over fan in, and okay, everything is okay. So for example, what happens if you scale everything that has fan in, you scale it by, let's say, fan in square, and then fan out, you scale it square as well. Like what happens if you start playing with those
Oh, okay, I see. Okay, I think I understand what you mean. Like you're saying, okay, maybe like let's scale down like the body of the network, like initialization learning rate by a factor of fan in or something, like by factor width or something like that, and then scale up the upper layer by the same factor, right? Yeah. So that would essentially be the same, right? Like mathematically speaking, the function evolution will be exactly the same. The reason we're choosing this particular way of scaling is because this keeps the activation scales to be constant size as with increases. So your way of scaling would like make the activation scale like 1 over width or something like that, right? So that would decay to 0. I mean, like if you have perfect precision, that's fine, right? Like if you have like flow 64, you'll be fine for a while. But if you're thinking about like large model training today, it's mostly using like half precision, and there you really want to keep activation scale consistent as you change width. So that's the choice we made.
Okay. And I have another question. What happens? Did you try using orthogonal initialization? Because
it doesn't change. Yeah, that's fine. It doesn't change it's the same scaling as this.
But
I mean, you would go ahead.
When you use orthogonal initialization, you don't scale the weights, like they are fixed because they are just an orthogonal matrix. So you
no, but you can still scale the weights, like as in you can make it larger and smaller. You just sample from orthogonal distribution, and then just scale the weights, right? That's kind of like here we're just talking about what should be the scale of the initialization, right? You can still scale the orthogonal ones, even though they're not going to be like orthogonal in terms like W times W transpose equals I, but you'd be like W times W transpose equals I times some constant squared.
Okay. Okay.
Yeah, but you'd be the same scaling law as this.
Okay, thank you.
Mm-hmm. All right, so I'm almost done. So let me finish and we can discuss more questions. Yeah, so here I just want to briefly talk about tensor forms, which is like the mathematical framework underlying all of this. So I'm going to be fairly brief here because I don't want to get boiled down into like all the rigorous mathematics here. But the first question you probably asked is like, what is a tensor program? And at a very surface high level is just a kind of computation that's composed of matrix multiplication and quantized nonlinearities. But there's like a formalization of this concept, which takes a bit to explain, so I won't do that. But the key insight, the first key insight here is what I'll call the Turing thesis for deep learning, which is that any useful deep learning computation can be expressed as a tensor program. And based on the surface level description, this sounds almost trivial, right? Because like isn't that just any deep neural network is matrix multiplication and quantized nonlinearities? And when you do backpropagation, you can see that it's also composed of the same things. So this is like by itself, this Turing thesis for deep learning is almost trivial. But what's not as trivial, or even what's surprising here, is that you also have this key insight too, which is true, which is that you can take the infinite width limit for any tensor program. So in particular, you can prove like a master theorem that reduces the calculation of infinite width limit for any tensor program to a set of mechanical calculations. And you can think of this master theorem for infinite width limit as like in the same way as autograd is for gradients, right? Autograd kind of makes differentiation for any computation graph automatic. And likewise, master theorem makes taking infinite width limit something that's quite automatic, even though like at least like mathematically it's automatic. So as an example, to derive like to put in context all of this, like the previous kernel works in the feature learning limit, one way to think about it from the framework of tensor program is the following. So if you look at NNGP, from a tensor program perspective, what you're doing there is just you're writing out the first 4 paths of the neural network on the data in this form, this tensor program, and then you just take in the infinite width limit of that. And essentially, roughly speaking, that's the NNGP. For next step for NTK, essentially it's the same, but you slightly enlarge the program to write also the first backward pass, and then you take the limit of the first this program of first 4 and the first backward pass, and you get NTK. Like roughly speaking, that's what happens. And the feature learning limit, essentially you write out the entire training procedure, not only initialization, but all 10,000 steps of HT or whatever, however long you're training it, and you take the limit at the end. And before TP, this is quite hard because there's not a very universal way of understanding what happens during training, like how does randomness during initialization propagate during training. But with TP, this is almost trivial because once you write down the program, you can just kind of like you can just call the master theorem on the program and you're done. I mean, of course, like you actually have to do the calculation, but you really like as a thought process, it's actually quite simple. All right, so that's all I'm going to say about TP as a technique. But here I'm just going to briefly give you like timeline of the TP series. So yeah, I started working on TP essentially last half of 2018, and then I essentially spent 2019 to 2020 writing the foundation papers for TP, which will later be used for TP4, which introduces mu p and the feature learning limit, and now TP5, which gives you transfer. And yeah, so actually like TP4 and TP5, the concepts and the like I kind of knew that they would have a good chance of working like very early on. For example, for TP5, actually, like me and Edward kind of like finished all the basic experiments on TP5 that convinced ourselves that it works before I actually started writing TP2. And in particular because I was like really tired of writing, so I was trying to do something else. So that took a while to come to fruition, and I'm pretty happy with the way it turned out. Anyway, I think one point I want to make here is that like the practical usefulness of all this thing is like pretty much nil until TP5. And I want to, I don't know, like for younger audiences, I want to kind of point out that I think long horizon research still has a lot of value if you can see like a vision, and you can like work on it for several years and see a payoff at the end. And I hope, I'm not saying like our work is particularly great or anything, but hope like that encourages some younger researchers to do these long horizon works. Okay, so I'll conclude here and then I'll open up for questions. So what I want to do looking forward is kind of a theory of everything for scaling. So as an example, our work proposes the hyperparameter transfer problem, but also solves it with in a principal way, in a theoretically grounded way. And the question is, can we do it for all other complete hyperparameters like depth, number of experts, and so on and so forth? In our work, we empirically evaluated these things using naive methods, and they kind of work within reasonable scales. But as we go to larger scales, probably they will break down, and we need like a principal way of thinking about them. And yeah, we want to verify the optimal scaling thesis for these complete hyperparameters. And this is akin to the search for a theory of everything in physics, where I analogize the different scale or complete hyperparameters, different fundamental forces of nature. And we're looking for a theory that tells us how to scale every aspect of the model together, just like physicists look for a TOE. Here's a typo. But yeah, so that's all I had. Thanks everybody for listening. And yeah, here's the paper link and QR code. And if you want to use our library, here are ways to either pip install or you can get Gitcon.
Yeah, thanks a lot for this very interesting talk, Greg.
Yeah, thanks, guys.
Are there questions?
Greg, could you maybe give a little more insight one more time on the relation to NNGP? So just taking the simple case where the output weights pick up an extra factor of 1/n in the variance. I mean, the kernel, if you'd like, the 2-point function going to 0 in the infinite width limit. So it's like at initialization, you're localizing on one particular type of configuration or something like that. The uncertainty is 0. I don't know. Can you just comment a little bit more on how I can think about this from the perspective of taking something we know very well, like an NNGP, and then picking up this extra factor of 1/n?
Yeah, I mean, like initialization, I think what you described is it. Like, there's nothing more complicated. You're just shrinking the variance. So in the NNGP configuration, the variance is becomes constant as you go to the infinite with limit. And here I'm just scaling that down to 0 instead of like at a rate of 1 over square root of n. So the variance will be 1 over n as you go to the infinite with limit. So we're saying, okay, we don't actually care about the initial GP, like the uncertainty. We don't care, like that doesn't matter for us, and we're only focused on the training. And like maybe you're wondering, okay, is this necessary? Can we have the GP but also like train well? And as a consequence of the dichotomy theorem, you actually cannot, like it's a dichotomy between, if you want to have like a non-trivial GP initialization, then you will suffer break, like a divergence during training if you want to get some kind of feature learning. So it's like a either or exclusive.
Fancy. Thanks a lot. Well, I'll see you in a week or 10 days and we can talk more.
Yeah. It sounds good, man. Yeah, can somebody read the questions? Zoom, the interface is not working for me.
There's about 400 questions, so we'll be here all night.
All right, so maybe can I go from the very recent to the top? So okay, Havu Tran says, I'm trying to understand practical limitations in EP. Seems like it's suitable for all CNN-like and transformer architectures. Table 3 won't work for depth-wise convolution, right? So I don't know what depth-wise convolution is. Is there a more robust way to know which hyperparameters are transferable? So yeah, I thought a lot about if there's easy, if you really want 100% law for determining which hyperparameters are transferable, is there easy way of describing it? But I would say I think it's not so easy to draw a black line somewhere. Yeah, I would say if you have some hyperparameters in mind, and I can tell you what I think should be the case. But I mean, usually the things we have in the table, like learn rate, momentum, initialization, these things cover most of what people want to do in practice. Okay. Just going through the comments. Okay, maybe Edward has answered all the outstanding questions.
Yes.
Greg, what did you say?
Oh, did you answer all the outstanding questions in the chat?
I don't know. I just got here. I had a meeting from 1 to 1:30.
Oh, okay. Well, okay. Anybody who haven't had their question answered, you want to shout it out or something? Yeah, there's a lot of messages in the chat.
About diffusion learning and kernel regime dichotomy, is the lack of kernel regime a problem?
Is the lack of kernel regime a problem?
Yeah, I'm trying to understand. If that implies that the function will not converge in the function space, or it just converges with a more complicated way than the...
You mean in the feature learning, you mean this, when I say function evolution cannot be described purely in the function space, what that means? Is that the question?
Yeah.
Yeah. So essentially, you need to keep track of like some description of the weights of the network. So in particular, like you can construct examples where in the feature learning limit, like two functions, two neural network have the same function in the limit, but they will evolve differently, right? So if your function evolution is purely described in the function space, via this kind of equation, for example, but like any kind of equation that only depends on ft, right? Then like for any if your neural network looks like this kind of function, then you evolves like this other kind of function in the next time step, and so on and so forth, right? It does not care about like what the internal state of the network is. But in the feature learning limit, it really does care about the internal state of the neural network. So like, what does the weight look like? Because you can construct a counterexample where two neural networks, two different neural networks are different weights. They are the same in the function space, and they will evolve, according to different trajectories in the function space. Does that make sense?
I see. Yeah, thanks.
Mm-hmm.
Is there something to that figure in the sense of what's the logic with putting these dots somewhere, or to the shape, or is this?
Yeah. So yeah, you can formalize everything so that it's in like a modular space, if you will, and the natural coordinates of the space is like essentially like the exponents of how you scale initialization and learning rate. Okay, let's just say these two, and then this non-trivial portion of space is actually really a polyhedron. So it's it has facets, and it's like determined by some intersection of half planes, and the neural tangent parameterization really is a vertex in this polyhedron, and the maximal out-of-date parameterization really is a vertex in this polyhedron, and like the feature learning parameterizations really are formed by two facets of this polyhedron. So that's all true. Yeah, I think standard parameterization is on the edge. It's on the edge in the higher dimensional polyhedron.
I see. And that's essentially in the tensor networks 1 to 4, effectively.
Yeah, that's in TP4. Yeah.
All right, final chance. Questions? Not, let's thank Greg again for a very interesting talk, and let me stop the recording.